Today, we will be talking about partial fractions, whatever that means, okay? But, and let me just make sure I'm sharing the right thing here. So new share, yeah, I'm sharing my screen, that's great, okay? Which sounds exciting. You'll see what that has to do with here in a minute, but I thought that we would start with a little warm-up problem. So let's do that first here, okay? So here we go. And by the way, the reason I gave you those whiteboards was because a lot of times I'll have you work on stuff, and it's not always the most helpful thing on your notes to just have some disastrously wrong thing in your notes, right? I mean, you could sort of make a little marginal notation that says, hey, this is wrong or something. But the whiteboard gives you some space to kind of play around with things, think things through on your own. So I do encourage you to bring those whiteboards and use them as the opportunity presents itself. But here's the problem I want you to work on right now with people around you, okay? It's the following, okay? It's gonna be a little bit tricky, but I'm gonna tell you what to do. I'm gonna tell you what to do, okay? So here we go. Integral of what? Get rid of that thing. Of the square root of 1 minus x over the square root of x dx. Okay, and I'm going to tell you, this doesn't quite look like what we've dealt with before. Typically, we've had like, you know, a difference of squares. Do you understand? Like we've had, you know, 1 minus x squared under the radical. So before I turn you loose on this, what do you think would be an appropriate trig substitution here to turn it into something that we do know how to deal with? What do you think? Yeah. So I mean, so yes, if you let x equal sine squared of t, you're like, what? I can do that? Sure. Why not? We can do that. But that's the same thing as saying that the square root of x, if you think about it, that's the same thing as saying the square root of x is equal to what? Sine of t. Okay? So then what is, well, I'll leave you to it then, okay? So you'll have to figure out what dx is, okay? You have to figure out what 1 minus x equals, etc. But that's kind of these two, this observation of putting x equal to the square of sine, which means that really we're putting the square root of x equal to sine of t is really the key to getting started. So I'm going to let you work on that for, you know, 10-ish minutes or so, okay? So go for it. Okay, so that wasn't quite 10 minutes, but I'm curious to see what kind of progress we've made. So what's dx? Can someone help me get dx from this? Yeah. dt or whatever, right? Yeah. So dx is like, this is thing squared, right? So I have to use the chain rule. So 2 is going to come down, sine of t, so 2 sine of t to the first times the derivative of sine of t, which is cosine t. It's going to be 2 sine of t, cosine of t, dt. Okay, good. And what's 1 minus x equal to in this case? Yeah, 1 minus x is actually 1 minus sine squared, which is, by design, cosine squared. Beautiful. So what's the square root of 1 minus x? Yeah, that's cosine. Amazing. All right. So we go over here. Okay. And we just plug in all the things that we have. Okay, it's going to be cosine of t over sine of t. Excellent. Dx is simply 2 sine of t cosine t dt. And the sines cancel. Right? And what do we end up with here? I will make you one way or another remember some stuff, right? So 2 comes out. We have the integral of cosine squared of t dt. What do we do? Half angle. You got it. All right, so remember the half angle formula, cosine squared of t is 1/2 1 plus cosine of 2t. Okay. Now the 1/2 and the 2 conveniently cancel. And this just ends up being the integral of 1 plus, right? So, I mean, just so you know, I'm taking this guy and I'm putting it right there. Okay. I put this guy right there. What it's equal to at least. Okay, so then it's going to be 1 plus cosine of 2t dt, which, again, it's very important to keep track of your variables, yes? The fact that we're integrating in t right now is critical. What's the antiderivative of 1? T. Okay. And then it's plus, what's the antiderivative of cosine 2t? Yeah, 1/2 sine of 2t. And now what? Huh. Now what? I need to go back to x, yes. So back to x. How to do it? Okay. So first of all, what's t equal to? Let's go up here to the top. What's t going to be equal to when all is said and done? If I go back to the original thing, which is that the square root of x is equal to sine of t, what's t? Arc sine of the square root of x, which is sort of weird, right? That's all right though. Now, but I don't know what sine of 2t is per se. So what am I going to use? What do you think? Yeah, double, right? Sine of 2t equals 2 sine of t cosine of t. Where's okay. Where's cosine of t? Well, or I just have it right there, right? I already figured out what cosine of t was. It's the square root of 1 minus x. Yeah. Okay. So let's see here. If I plug this guy in right there, clearly the 2 and the 1/2 is going to cancel, yes? And I'll just have sine t cosine t. So I'm going to have t, which is arc sine of the square root of x, plus the 2 and the 1/2 cancel. It's going to be sine t cos t, which is interestingly the square root of x times the square root of 1 minus x, which I could just write as, yeah, I could either write it as that or just as x times 1 minus x, right? Or I could write the square root of x minus x squared, yes. And this is all, of course, I forgot the plus c, okay, which is critical, right? Okay. All right, questions on that? Yeah, Daniel. What? Say again. Where did I get?
So where did you get
the 2? Well, that you mean this 2 right here?
Yeah. So you have 1/2 back to x, and then you don't have.
Yeah, that 2 came from right there in the double angle formula. You see that? Yeah. Mara? Because, okay, yeah, so because you see this up here, Mara, the square root of x is sine of t, yes? And so that goes right there, yeah? And what about the square root of 1 minus x? What's that? So this is just, this whole thing is just 2 times the square root of x times the square root of 1 minus x, which I just decided to write under a single square root. Does that make sense? Yeah. Okay. Other questions? All right. Let's do this then. Partial fractions. They fixed the bulb, which is fantastic. Okay. So let's do this thing. Partial fractions. Here we go. Okay. Hold on to your, your seats here. Okay. So this is this one. I think we can basically turn it into a mechanical process again. That's not to say there's not going to be times where that's challenging. There's going to be some algebra involved in doing that. But here's kind of a warm-up exercise for us. Okay. What about the second thing that's sitting right there? Do you know how to do that antiderivative? Like immediately? Yeah, it's like 1 over x minus 4. What's the antiderivative of 1 over x minus 4? Because it's like just a single x like that, I don't have to do any funny business. I could do a u sub if I wanted to, but I would realize pretty quickly that the antiderivative of 1 over x minus 4 is just logarithm of x minus 4 in absolute value, yes? So the second thing here, that works out pretty nice, right? Okay, so let's see here. So this is equal to the natural logarithm of what? Absolute value x minus 4 minus natural logarithm of absolute value of x plus 1. Which, by the way, if I really wanted to be extra cute with this thing, I could say, well, that's just the natural logarithm, absolute value of what? Yeah. X minus 4 over x plus 1, just using the laws of logarithms plus a constant. But the whole point is that second integral was easy, right? I mean, that's something that was easy to handle, okay? Now, what about the first integral, though? What do? Now, one thing you might be tempted to do, based on what we did in like the first section of chapter 8, is to try to complete the square. Do you know what I'm saying? But if you try to complete the square, okay, I mean, look, how would you complete the square here? I'm going to write this up here just so that we can see it. How would you complete the square of the bottom? So let's do some work up here. X squared minus 3x minus 4. Do you guys remember how to complete the square? Divide the x term by 2, which in this case is fairly nasty. That's 3 halves, yes? Negative 3 halves. And then add and subtract the square of that. So 3 over 2 squared, what's that? 9 over 4. So okay, yeah. So this would be x squared minus 3x plus 9 over 4 minus 9 over 4 minus 4. That's interesting. Okay, and I can actually complete the square now. So what is it going to be? X minus, help me out here, x minus 3 halves. It's the thing I got from dividing that term by 2. X minus 3 halves squared takes care of all this stuff right here. That takes care of all this stuff right here, yeah? And then what do I have left? Minus 9/4, minus 4. 4 is the same as 16 over 4. You know what I mean? So this is going to be minus what? Minus 25 over 4. But the problem is, that is not, well, now look, that's kind of what I would try to put under, like down in the denominator, yes? But that is not of the form of something that I know how to handle. Do you understand? Before it had to be a number, a positive number, plus something squared, remember? And then I knew I could invoke which arc function. Arctangent would do the job. But the problem here is I don't have plus a positive number. I have minus a positive number, and I go, what am I going to do? Well, here's what we do. You ready? Watch. Here's what we do. First thing you do is you factor this thing right here, okay? You factor it. Okay, we already kind of did a completion of the square thing that didn't end up bearing much fruit. So I'm going to put a big yellow X through this and say, well, that didn't help. The reason it didn't was because of that thing right there. It was negative. Okay, so I'm going to factor this thing. Okay, so so I'm going to factor this thing. Okay, in so doing, I'm going to get the integral of okay, dx. And then you start thinking, wait a minute, I just did an integral that was kind of, I just did an integral that had like an x minus 4 and an x plus 1 in it. You know what I'm saying? In fact, let's just think about this for a minute. You see these guys right here? What if I were to combine them? How would I combine these things? Okay, if I were to combine these things, look at what I would get. I would have to multiply the first thing by x plus 1 over x plus 1. I would have to multiply the second thing by x minus 4 over x minus 4. And I would end up with the integral of x plus 1 over, right, let me do everything at once. X plus 1 minus the quantity, I would have to multiply the second thing by x minus 4 over x minus 4. All over x minus 4 times x plus 1. Okay? And what does this stuff turn into, amazingly? This stuff turns into, right, the x's cancel, and it's going to be 1 minus negative 4, which is 5, which you say, oh my word. Right, and this was a dx, by the way. You say, oh my word, these things are equal to each other. This is equal to that. Okay? And what that motivates us to do is to learn how to go backwards. It was easy for us to combine those things by finding a common denominator, but it's not so easy to go backwards. Does that make sense? Okay, so let me just erase something right here. Let me erase this junk right here because that's no longer helpful to our task. Okay, what in the world? This thing is taking a while here. Okay, so here is our goal. Here is our goal. Okay, learn how to see that 5 over x squared minus 3x minus 4 is indeed equal to, because if I could somehow transform this into the other thing, I would be good. Does that make sense? I would then be able to do the integral. Learn how to see that that thing equals 1 over x minus 4 minus 1 over x plus 1. You see what I mean? Because then I would be able to do the integral. Yeah? And this thing right here, I'm just going to tell you, doing this sort of thing that is sitting right here, that's referred to as, this is referred to as a partial fraction decomposition. Partial fraction decomposition. Decomposition, right? Because you basically are decomposing one fraction into a pair of other things that are easier to deal with, at least as far as integration goes, yeah? But still, we need to figure out how is it that we can actually see how to do this, how to break this thing apart. Does that make sense? That's the goal. I'm going to pause right there. Any questions on this so far? I haven't told you how to do it, but that's the goal. So any questions on this so far? Questions? All right. Let's clear this, and I'm going to show you how to pull this off. Are you ready? Okay. So here's how you do it. Watch this. Okay, I'm going to write it. I'm going to write it in blue. Okay. Okay. So 5 over x squared minus 3x minus 4. The first thing we did is we factored the bottom, so that it was 5 over, what was it again? X minus 4 and x plus 1. And what you can do is you can say, look, this has got to be, there's got to be a way to break this up into a number over x minus 4 plus another number over x plus 1. Yeah? So I want to write this as something over x minus 4 plus something else over x plus 1. Okay? That's the goal. You know what I'm saying? I want to write it as something over x minus 4 plus something else over x plus 1. And these guys right here are just, right, this, and this, these are just numbers. Okay? Numbers that are unknown to us. Yes? Well, the reason, yes, it must be able to be broken up into that, but the reason that is because the power of the numerator of this thing, the power of the numerator of the original thing is less than the power of the denominator. Okay? If that was not the case, what do you think I would do as a first, like, initial step? Like, suppose the power of the numerator was bigger than the power of the denominator. You would do polynomial division to ensure that happens. Does that make sense? Because if the power of the numerator is smaller than the power of the denominator, then it's guaranteed that that's still going to be the case even when I break it down. Okay? When I break this thing down, the power upstairs would have to be smaller than the power downstairs. Yes. You just have to be able to factor it, right? But the issue is sometimes, and we'll talk about this soon, sometimes you won't be able to get it down to linear factors. Linear factors are things that have a highest power of x. Sometimes you'll have second degree polynomials that you cannot factorize anymore. They don't have any roots. Does that make sense? Like x squared plus 1, for instance. You can't factor that unless you go into the complex number realm. Does that make sense? So that will happen from time to time. But the goal is to factorize as much as possible and then break the thing down. But you always want to decrease the power upstairs where it's below the power downstairs through polynomial division as an initial step. Okay, but that's something we'll have written down here pretty soon anyways. Okay, how do I find A and B? How am I going to find these things? How do I find this and how do I find that? Well, what I like to do is that thing that I just boxed in red. I like to clear denominators. Okay? So I like to clear denominators. What do I mean by that? I want to multiply everything by, okay, what could I multiply by that would clear the entire collection of denominators? x minus 4 times x plus 1. I'm going to multiply everything by x minus 4 times x plus 1. Okay? So what I'm saying is this guy is going to go here, it's going to go here, and it's going to go here. Now it's really that first thing that's the one that really helps me out. So like if I distribute this thing through to this equation, what does the left-hand side become once I do that? Right, it's just 5. Oh my goodness, right? 5 equals, okay, what does that a over x minus 4 become? A times x plus 1. And what about the second thing? So it's plus b times x minus 4. Okay, what I'm really doing here is finding a common denominator. You guys realize that if I were finding a common denominator, I would have to multiply a by what? What would I have to multiply a by? X plus 1. And what would I have to multiply b by? X minus 4. And I'm saying once I find that common denominator, the numerators have to be the same, yes? Okay, so what I'm really doing here, I'm just going to write this here, is I'm really comparing numerators. Comparing numerators is where this really comes from. I mean, I talked about it as clearing denominators, but when I do that, I'm literally comparing numerators. And they have to be the same thing, yeah? Okay, someone had a hand up. Over here somewhere, I saw a hand go up. Nothing? Okay. Okay, what to do? How can I figure out what A and B are? Remember, the goal is that I need to know what A and B are, right? I want to know what A is. I want to know what B is. How am I going to pull that off? There's actually, well, yeah, there is a way to kind of get some equations you can compare things with. But there's also, in this case, there's actually an easier way to do it by simply plugging in values for x. So for instance, I could plug, and you plug in things that are convenient. So you can plug in, like what if you plugged in x equal to minus 1? That's going to kill the A thing. Does that make sense? If I plug in x equal to minus 1, what does the left-hand side turn into? 5. That doesn't change at all. That's still just 5. What about the right-hand side? The nice thing is it kills off A, and then it's going to be minus 5b. So what's b equal? B equals -1. Okay? Okay, and then what's another thing I can plug in? Yeah, why not? I can plug in 4. Okay, I plugged in x equal to minus 1 and it got me b. If I plug in x equal to 4, of course the left-hand side doesn't change, it's still 5. Yeah? But what does 5 equal? If I plug in x equal to 4, I get the b part dies, yes? But you get 4 plus 1, which is 5a. So what's a equal? 1. Make sense? Amazing. So that means what we have shown in essence here is that this guy right here, after we do all the factoring and then we kind of set this thing up and try to figure out like how to break it apart, we figure out that this guy is equal to this guy right here, just as we suspected. These two things are equal to each other. This guy right here is A, right? That's our A, and this -1 thing, what's that? That's B. You know what I'm saying? Yeah? There's our A and there's our B. Yes? Yeah, and yes, in essence, that's what's happening here. So let me just, okay, I'm gonna go over to another screen and I want to show you two different ways to do this, okay? There's actually two different ways to do it. Okay, so are we good to go? Any other questions on this? Okay, want to clear this. Okay, so watch this. I am going to share the whiteboard here. Watch this. Here we go. Okay, so watch. 5, oops, I don't like that. I don't like yellow. Okay, 5 over x squared minus 3x minus 4. We figured out that that was equal to 5 over x, what was it, x minus 4, x plus 1, yes? And then we wrote this, now can somebody tell me in the notes, did we write it as a over x minus 4? Yeah. Plus b over x plus 1, okay? A over x minus 4 plus b over x plus 1. We cleared denominators, yes? Okay, we multiplied everything by x minus 4 times x plus 1. Okay, which means boom, boom, boom. It goes to all three of these things. Okay, and I ended up with 5 equaling a times x plus 1 plus b times x minus 4. And the first thing that we did to solve this, right? So again, the goal is to figure out what a and b are. The first thing we did is we plugged x equal to, what was it, minus 1? And if you plug x equal to minus 1, we got 5 equals negative 5b, which means that b is negative 1, right? So that was the first thing we did. The second thing we did to sort this out was to plug x equal to 4, which told us that 5 is equal to what? 5a, which means that a is 1. And we were in business. But there's another way. So this is what I kind of call, this is called the plug-in method, okay, to kind of solve these things. But there's another method. There's a method that I like to call the compare coefficients method. And I want to end with that. So here's how that works. Look, do you guys see up here, I have 5 equals a times the quantity x plus 1 plus b times the quantity x minus 4, right? Look, if I were to kind of combine things, if I were to distribute a through here and b through here, I would have x times something. What would x be multiplied by? Think about it, it would be ax plus bx, right? And I could factor x out, so what would that be? A plus b times x, correct? And what would I have as the constant term? That's like the x term, but there's also a constant term here. What would the constant term be? A minus 4b, see what I'm saying? Okay. So in other words, I know that 5 has to be equal to a plus b times x plus a minus 4b. That's interesting because there's not an x on the left-hand side. Do you know what I'm saying? But I can actually write this as like 0x plus 5 equals a plus bx plus that other thing. So what do you think has to be true about the coefficient of x over here and the coefficient of x over here? What do you think has to be true about those two things? Since they're equal after all, those have to be the same. Yeah? And in addition, 5, what does 5 have to be equal to? It has to be equal to the constant term. So the x stuff has to be equal, the constant stuff has to be equal. That gives me 2 equations. Do you know what I'm saying? I know that 0 has to be equal to a plus b, but I also know what? 5 has to be equal to a minus 4b. And now you're back in 9th grade algebra, aren't you? You have 2 equations and 2 unknowns. How would I solve these things? What would you do? You could solve, I mean, you could like take the first thing right here and solve. You could say that a is like, a is equal to, like the first equation says a has to be equal to what? Negative b. And you could take this guy and put it right here. And then what would happen once I did that? You would get 5. Oops. I'm starting to run out of room down here on the bottom. You would get that 5 equals what? Negative 5b, i.e. b equals what? Negative 1. But then once I know b is negative 1, guess what? I know what a is, right? If b is negative 1, I know that a has, because a is negative b, a has to be equal to 1. See what I'm saying? The reason I'm telling you this is it's not always going to be possible to figure out everything by plugging stuff in. This example, it was possible to do that. You know what I mean? But that's not always going to be true. There are going to be times when you're going to have to resort to comparing coefficients. So you want to have both these tools in your back pocket. You want to plug in is an easy way to get some of the stuff, but then comparing coefficients is something that you might want to resort to when you run out of stuff to plug in. Does that make sense? Okay. There's a lot more to come. We're going to do lots of examples of this sort of thing, but this is kind of how this is going to start. The plug-in method and the comparison of coefficient method, those 2 things are going to be the key to solving integrals of this type. Okay? Any questions? All right. That's it.